Thank you, Marisa. So, so I work at Nvidia, and many people know about Nvidia as a company that makes the processors for graphics cards, or GPUs. And obviously, we're heavily invested in computer graphics, and computer graphics is a big piece of what I'm going to talk about today with AR and VR, or just sort of generally XR, extended reality. What is maybe less well known is that Nvidia also works on, in addition to powering video games and scientific visualization and all those things, a lot of effort in Nvidia, it goes into software platforms and hardware for artificial intelligence, for robotics, for self-driving cars, avionics, and other fields like that. And especially, obviously, cloud computing has become a huge factor in all of these industries, and I think it's going to be very important in the future for AR and VR as well. It's a sort of an answer to the question of how do you move computation and power off of somebody's body while still giving them a great visual experience. And the answer has to be that somehow that's being communicated across 5G or something and processed at least partly in the cloud. So all of those areas that NVIDIA are working in, I think, come together. But I wanted to express that we're not just a graphics or a rendering company, nor is what I work on graphics and rendering specific. And in fact, Nvidia Research, which is the part of the company in which I work, there are about 14,000 people in the entire company, and there are about 140 research scientists. We're spread all around the world, and we work in pretty diverse areas. So there's a great compiler group, as well as a great circuits group. There are people working on machine learning, machine vision, all those sorts of problems. And within the specific group that I work in, which is graphics systems, for new experiences and sort of visual computing, there's also a lot of different things that we focus on. So we think about problems that involve these issues, like how do we provide a responsive interface, whether that's 3D or 2D or some kind of like haptics, non-visual feedbacks. There's low latency, high throughput on that. Our group is responsible for anything that has new kinds of input and output. So forget about mice and controllers and keyboards and monitors. That's an area that we understand well how to accelerate computation in that space. Let's think about all kinds of new ways that you might interact. And in general, we describe it as graphics systems that are beyond the microchip, which has been NVIDIA's historical core competence within graphics. And I think the most important part of the graphics system that's beyond the chip is that the person using the system is not inside the microprocessor. And so often, a lot of the questions that we have aren't solved just by technology. They're solved by understanding perception and people and space and psychophysics as much as building technology to adapt to those systems. And that's really, I think, at the forefront of computer graphics. We've hit the limits of what can be done by brute force and by scaling and Moore's law. And so graphics now is about really understanding what we're trying to create and not just brute forcing a physical simulation anymore. And of course, as you might imagine, to work on those sample applications and those issues, within our graphics systems team, we have a really diverse set of expertise as well. So these are all the folks that I'm currently working with, and I would say probably a minority of us have computer science degrees, or even electrical engineering. So there are people who have a background in art, or math, or psychology, or mechanical engineering. And part of what makes systems so exciting is that almost everybody is coming from a different field, and we're all interested in this sort of interdisciplinary work that can solve problems that are too hard if you just look at sort of one academic silo, but it's really the solution is going to come between two spaces. So what happens when you put holography and perception and data structures together? Suddenly you can do new things and create new kinds of displays. Within the set of things, narrowing down from everything NVIDIA does, everything our group works on, to just the topic, or specifically the application domain of extended reality, there are a lot of different areas that I think are interesting and that have different names, which in some cases just came as a marketing group was maybe trying to distinguish a new product. But I think these are actually useful distinctions. So this is a screenshot from, this is not an actual display, this is from the Sherlock television show. But we would call this labeled reality. So this is showing you what Sherlock sees as he's sitting there. Actually, that's Sherlock. So this is probably Watson or someone. But this is a text message. And imagine that instead of it being on a phone, it's just you sort of see it in the world. right? Or you just see a label on something saying, well, this drink has this many calories, or actually that has peanuts and you're allergic to peanuts. So that's labeled reality. We're taking the real world, we're not drawing complicated new 3D things, we're just sort of annotating the real world, like putting little labels on things. Augmented reality, we would cast as the case where you're in the real world, you're interacting, but we have some virtual objects that we can manipulate as well. So the screenshot from Iron Man gets there. Mixed reality is often talked about in the design context, where we don't want a lot of small artificial things. We want to put one realistic looking object that we're all going to work on together, and it's the value of having a shared space. Traditionally, if you're working on a car, you might have a clay model that's a physical object, but it takes a really long time to build a car, a full-scale clay model of a car. And if we could do that using computer graphics, obviously that would be advantageous. And then full-blown virtual realities where we've just completely removed the real world. So maybe there's still a tactile sense, maybe there are physical walls or props that I can hold, but everything I see, everything I hear, and maybe even some other senses is being replaced digitally. So there's sort of a spectrum of how much of the real world are you blending with the virtual world. And there are interesting use cases along the way and sort of different technology choices you would make. And I think having those as, I call it a spectrum, but I think those discrete cases are kind of interesting points where they're sweet spots because they map to tasks that people are already doing. Let me briefly tell you about the way that extended reality works today. On the side, I'm showing you two displays. These are both augmented reality, and they're sort of the best along some axis. Focals by North, which is, of course, North is based in Kitchener, and they have an office in Toronto as well, is trying to make glasses that look as much like regular prescription optics as possible. So there's nothing computery about them. You don't see them glowing. There isn't a big cord coming out. And in exchange for that, they sacrifice an awful lot on visual fidelity and features, but they've really nailed the form factor. HoloLens goes exactly the opposite way. So this is not virtual reality. This is an augmented or mixed reality where I can see the real world still, but in order to give you a really powerful processing and to give high quality graphics, there's a heavy computer and a battery, and there's a complicated set of lenses on the front. So they've sacrificed the form factor in order to increase the quality of the experience in other ways. The way that all of the head-mounted displays in other XR systems work today is that there are either camera trackers or inertial trackers or both. You can think of an inertial tracker as it measures acceleration. It's like a little spring and a weight, and as something moves, it says, oh, I'm accelerating a direction. So it's very good for small, sharp movements. It's not very good for long, slow movements. That tells us where your head is and if you're holding an object where your hands are. There's a little bit of work, most of it not super robust yet, on commercial products that could track your hands or your body without holding objects. Today, the state of the art is for reliable input, we need you to physically hold something and physically wear something. So that's how we know where the person is. And then there's a display somewhere near your head. For virtual reality, it's a cell phone panel that's very close to your face. And then there are lenses that are like, it's like if you took binoculars and flipped them around, so you made everything farther away instead of closer. And that's what allows you to focus close, is that we've optically moved the objects about 1 or 2 meters away from your face so that you can focus well. That's how virtual reality displays work. That's why they're big and heavy, is because they have big, heavy physical lenses as well as effectively a cell phone sitting up there. For augmented reality, like these displays, what most people are doing is putting a tiny laser projector on the side of the head or above the eyebrow, and then that's pointing down through a piece of glass. It's a waveguide. It's like a fiber optic. You shine light through it, and then at some point it just bounces the light out into your eye, and there's no occlusion. So if there's a virtual object and a real object behind it, I can see the real object through the virtual object. However, thanks to local contrast, if we make the virtual object really bright, it can effectively cover up, it sort of drowns out the information from the real world. So that's the current state of the art in displays. There's varying specifications. They go between essentially television video game rates and about twice that for frame rate. That's important because when you move your head, if we can't update the image fast enough, it feels like you're slowly dragging the world until the image updates. And so you get kind of sick if as you move your head, the world is moving in a jerky way. So you would like to have a very high frame rate. You would like to have low latency, which just means that update is coming quickly as well as frequently. And I'd say the biggest limitations, though, on XR today are this fixed focal depth and narrow field of view. Those lenses put the image at a specific depth. You can't change the depth at which you're looking. So even though you perceive depth because of other cues like occlusion or shadows and of course perspective projection, your eyes are seeing something that's focused at a fixed position. For virtual reality, that's unpleasant for some people, but often okay. We can get away with it if there are enough other depth cues. For augmented reality, it's a serious problem. If I have glasses, they're adding content to the world. So imagine I'm driving, there's a virtual street sign. But the street sign, I have to focus at one depth to see it. But then I need to focus at a different depth to actually see the pedestrians in the real world. And so that creates this huge disconnect where I literally cannot see the virtual objects and the physical objects at the same time. For VR, because I can't see physical objects, I don't care. So that fixed focal depth is a huge problem, as is narrow field of view. It's because of the physical constraints in the optics, it's much narrower for augmented reality displays like these. It's often 15 for the focals to maybe 30 or 40 degrees. That's a very small part of your roughly 210 degree field of view. You can actually see past 180 degrees. Your peripheral vision goes slightly behind your head. And if you're limited to only seeing in a very narrow range, for VR that's uncomfortable. It makes you feel like you're looking through a peephole and you have blinders. For augmented reality, it means that the illusion is broken. There are things that I can only see when I'm looking right at them, and if I look away slightly, everything else is there, but the label disappears. And in fact, I don't even know the label could be there because it's completely disappeared. I can't even put an indicator in my peripheral vision. So those are two huge problems today. And it basically comes down to all of the current designs, at least the ones I'm going to talk about, have taken some design axis and they've made it maximal. They've said, I'm going for the best possible form factor. But then you often have to sacrifice everything else, and that gives you a very narrow range of applications with which you can experiment. There are also, I'm showing VR, but this applies to everything. It's more important for VR. There's sort of different levels of physical interaction you can have. You can imagine a seated experience where the VR doesn't track my position at all. So I can sit here, and that's it. I can maybe rotate, but I can't really move very far. And that really limits the kind of experiences you can have. It might be good for certain professional experiences, but if you have a narrative experience that involves traveling or being embodied in a character, you have a problem. And you can see this. There are a lot of narrative experiences that to say, you are a robot that has no legs. You are a person in a wheelchair, because now we can at least give you locomotion while you're seated. You are floating in space, and so you can't walk because you can't get enough friction because there's no gravity local to where you are, and so you have to pull yourself with your... But there's only so many of these things you can pull out before the cliche becomes ridiculous. And so it's great for driving a vehicle, but then you'd like to get out of the vehicle. There's standing VR, and it turns out just standing up, even if you still cannot walk around, right? Maybe the tracking is limited, maybe I just physically don't have much space because I'm working in a cubicle. Just standing up dramatically increases your perception, your willingness to believe that what's happening is real in virtual reality, which is amazing. And this is one of those things that, you couldn't get this from first principles. It's a perception issue. So just allowing people to stand up allows them to perform better at VR tasks and believe in the world more. But of course, if you can walk, it's better. If you can walk a lot, like if I have an entire office or a gymnasium-style space, that's great. And if that space is an installation, like it corresponds to physically the space that I'm supposed to be in virtually, so that there is a wall, right, where there's a physical wall that I touch. It might look completely different. I might think that I'm on a space station, but having the ability to actually touch objects and get physical haptic feedback, that's a huge improvement. Although, of course, at this point, you're doing live action role playing, right? So you've only replaced the visual, but you had to physically build everything, so you've lost a lot of the advantages of virtual space. So that's the state of the art. What I'm now going to talk about for a couple minutes is just walking you through what's next, what's coming after the state of the art. And I'm going to try to emphasize non-Nvidia research and research that I wasn't involved in, because then at the end I'm going to tell you a little bit about some of the projects that we're actively working on right now. So on displays, I think the big new technology that's coming is that holography. So not holography in the sense of Princess Leia and Obi-Wan, that's a projection that's three-dimensional. So what a hologram is it's a small device. It's like a piece of film, and you get a three-dimensional image off of it instead of a two-dimensional image. But the hologram is the physical object. And you can make holograms that are what you want to see in the virtual world, which is hard. That's called dynamic holography, and that's a emerging technology at best. Or you can make static holograms that, because they're a three-dimensional way of manipulating light, allow you to take a big physical apparatus, like the multiple lenses, physical lenses within a single camera objective, or a telescope, or a complicated virtual reality optical path, and squish that down to a flat piece of film. So there are a number of different displays people have made recently with this thing labeled HOE, that stands for holographic optical element. This is actually somewhat comparable to a series of mirrors and lenses that would normally be maybe that deep, that we can squish into a coating that comes on top of a prescription optics. In this case, this is work by Andrew Mamoni and colleagues when they were at Microsoft. And so they've built this augmented reality display that uses complicated optics but fits into a good form factor. So that's a trick that everyone is currently looking at. A problem with this is it's very hard still to allow you to solve that focus problem. I'm still focusing at a fixed depth. I've taken the VR lenses and made them really small and transparent, so they're AR lenses. Some nice work, which doesn't apply to augmented reality yet, recently came out of the Facebook lab. This is their half-dome prototype, which I think they haven't published the details, but they have some blogs on it. What you're seeing in an animation there is they have a series of physical lenses, and they can effectively turn on and off the lenses with some electrical optical components. And so they take this stack of physical lenses, but they can kind of dial in computationally a variable focal distance without moving a physical object. Normally when you focus, you either bend a lens, like in your eye, and there's been work on actual flexible lenses, or you move a lens, like when you're focusing a camera. So when you screw the camera, nobody in this room except Linda has ever screwed a physical camera objective. Cameras used to not be on phones. They were a big box. You guys are with me? And people go like that. They're turning a screw and it moves the lens in and out. So when you move the lens in and out, you're changing the distance, you're changing where you focus. The problem with, and people have made virtual reality and augmented reality focus systems like that. The problem with both bending and screwing is that you have a moving object. And if you have a moving device on your head, it's going to get miscalibrated, it's going to turn to break. So the idea here is that you can have a variable focal distance with that no moving parts. So I think solving the varifocal problem and using holographic elements in order to create new displays are sort of on the forefront there. On the rendering side, there's a lot of interesting things going on. This is work that we did a little while ago on disaggregating, splitting a graphics system so that it could be done partly in a data center or a cell phone tower, and partly in a head-mounted display using like a low-power cell phone processor. With the idea being we could give you cinematic quality images, like really film level, not video game, but do it in real time on a mobile processor so that you could have augmented reality or lightweight virtual reality. And the interesting thing is, at the time I was at Williams College, and Nvidia headquarters is in California. And so we were actually doing this with a server that was on the other side of the continent. So we were computing the graphics and streaming them, and the idea was to do that so that you experience no latency, no delay, despite light itself taking quite some time to get across a continent. And so we did neat local processing for that. Also from Facebook's lab, I think one of the most exciting things is the use of machine learning to create, in particular, avatars. Making realistic faces, the most interesting thing you can do in any communication medium is just talk to another person. But talking to another person goes horribly awry if they look like a zombie. And especially if you know them, right? The representation had better be very accurate. And unfortunately, in virtual reality, that would be one of the so-called killer apps, is if you just could have virtual communication with anyone, anywhere on the planet, as if you were physically face-to-face, which we have the technology to do. I could put cameras in the room and just stream the video. The problem is I would get video of you wearing a virtual reality headset, which isn't very interesting, especially for eye contact, right? If you had one aspect of human communication you wanted to preserve visually, it would have to be eye contact. And so what people have found is that there are various different research approaches, but that they're all circling around. It turns out that instead of using traditional computer graphics, first principles of light simulation and 3D modeling and character animation, you can use machine learning to learn from a few cameras pointed at the face of someone or maybe some stress sensors to essentially optimize out and learn a model that can directly render that person's face without the head-mounted display. And some of the latest results are extremely compelling. I think you could tell them apart from a real video, but at least for me, they've crossed the line of this isn't uncanny anymore. I'm comfortable interacting with a person, and their hair looks a little bit weird in digital, but the facial expressions are captured. So that's definitely a huge part of the forefront. I want to call it, this isn't research work, but this is sort of just beyond what's commercially viable as interesting interactive experiences. And these are both, there's a ton of virtual reality chat rooms, right? It's, you go online and go to Oculus Store or whatever, and the hundreds of choices. These two are a little bit different. They're interesting. The bottom one was just announced by Facebook. It's interesting in that this is sort of the multiverse as envisioned in science fiction with a cartoony aesthetic. But what's super interesting is that they've done kind of what nothing except maybe Minecraft has ever really done in a virtual environment, which is put creation and interaction in the same space. Usually in virtual worlds, you have to choose between interacting with people and interacting with the environment. And so Facebook has said that they're going to, for the first time, sort of put all of that together, and that you're not going to have discrete experiences like now I'm sculpting and now I'm talking. And I think that's super important. A little, pushing more on the art side, so Max Weisel has done a number of apps. He made like Lady Gaga's Art Pop app, extremely well known in the digital art space. Half and Half is a virtual reality chat room, but rather than trying to present realistic humans and deal with all the problems that arise, Half and Half is interesting because it specifically, is anyone familiar with the video game Journey? Okay. Journey is a nominally single-player experience during which you encounter other characters who turn out to actually be other people who are playing the game, but it just doesn't tell you that. And you can interact with them in extremely limited ways. And those limitations actually sort of enhance the experience versus many of the anonymous online interactions we have. So Half and Half does kind of that for an explicitly massive multiplayer environment. The characters are these cartoony characters. They don't look like people in any way. There's no compulsion to make an avatar of yourself. They have really stretchy, wiggly arms, which means that when the distance between the tracked virtual reality controller and the head doesn't make any sense, either because something's gone wrong or because it's running too slow, it fits the character because the character has wiggly arms that can stretch to any length anyway. So they sort of design the character around that. And they modulate the voices based on, so when you get really small, your voice gets tiny. And when you get really big, you have a deep, loud voice. And it uses everything around the locomotion and the hand movement. Everything is sort of based around making sure your perception is comfortable rather than realistic. So everything about the way you move is not scaled one-to-one to the real world. It's scaled to what will feel good given the limitations of the technology. And I think that was just a brilliant design to say, I'm not going to try to make the real world and fail because of the current technology. I'm going to make a world for which current technology is optimal, even though that world might not make sense. And so you're sort of relying on the imagination instead of technology. There's a lot of work in haptics going on. A lot of it shows up either at the Computer and Human Interaction Conference or at the SIGGRAPH Emerging Technology exhibits. And most of these are around trying to give some sense of inertia or dynamism to static props. And so they have to do something to move because that's how physics works. But they open up little wings or they shift weights around. The idea being you can't see this thing changing. And so you're picking up the same stick every time, but sometimes it feels like a sword, and sometimes it feels like a shovel, and sometimes it feels like a flower because it's changing its shape or its inertia. And these are mostly probably not commercially viable ideas, and because they're a little bit on the fringe. But it's, at the same time, amazing when you try them out, and it feels compelling. It really feels like you're doing an activity in a way that just holding a static prop doesn't. So that was a brief tour of sort of what I think is coming next and interesting stuff happening throughout the research field. Let me tell you concretely about some of the work that our group is doing at NVIDIA. So already shipped in the current generation of what's called Turing architecture graphics processors is multi-view rendering. So if I have a head-mounted display, I need to render for binocular vision 2 eyes. So it's nominally twice as much work. And it turns out it's a little more than twice as much work, because often we do these planar projections for traditional planar displays. But if you have a VR display, it's sort of, you have this curved lens and a fisheye projection, so you kind of want multiple little planar facets. So you might get 8 or 16 views you need to render, and I'm probably rendering at maybe twice the resolution and 4 times the frame rate of a typical display. So you quickly get up to 10 or 100 times as much computing horsepower as you would need for like a desktop video game. Multi-view rendering lets you essentially take into account everything that's common between the multiple views and pay much less than, say, 10 times. So there's still a little bit of overhead. You still have to shade things a little differently, but it's a huge advantage. And that's already out there in hardware and it's starting to be used. Also already out there in hardware, audio is an incredibly important sense. So virtual reality, augmented reality isn't just about video. In fact, both Bose and Amazon, although in limited extent, have shipped augmented reality glasses that are not glass. I think they have glass in them, but there's nothing on it. They're purely audio. And it turns out you can create really useful, and in some cases even more emotionally powerful experiences using only audio. But you better be able to simulate the audio awfully well if that's the only cue you're relying on. And the same technology we use for rendering light to make images, you can use to render sound as well. And so that's now hardware accelerated on new GPUs. You can also adjust the level of detail of the texture and shading on new graphics cards. And specifically what you can do is you can say, well, if I know where the person's looking because I'm tracking their eyes, then the center area where they're looking and attending to needs a lot of detail, but I could probably save some processing by not shading somewhere else. And in fact, if the somewhere else is also moving fast, or maybe it doesn't have much detail or has a lot of visual clutter, there are all sorts of models you can use of perception to reduce the amount of computation. So there's hardware support for this today, and there's some of the low-hanging fruit like I just discussed. A really great open research question that we're looking at is what exactly do people attend to? What do they perceive when they're not attending to it, when it's not in their foveal area of their vision? And how much and in what ways can we degrade? It's easy to degrade an image by just going into Photoshop and making it bad. The interesting degradations are ones that will make it faster to create the content in the first place. For that walking problem, right, going from sitting to standing increases my experience. Being able to walk around really enhances my experience of being in a virtual world until I walk into something. So installations are fantastic. I'll talk a little bit about them at the very end. For most of us, if I have maybe a 3 meter by 3 meter area, which is what Vive and Oculus recommend for their home VR setups, you can fit that into like a reasonable study or a dorm room or something, but I can't walk very far in 3 meters. I can walk, about 3 meters before I hit something. So in this paper, what we did is we tackled the problem of how do I make it so that if you're inside of this tiny 3 meter space, you think you're in a bigger space, or even potentially an infinite space. When you look at something, your eye moves, and then it jumps. So it's called a saccade. There's one case where you're tracking like a moving car or something like that. But normally when you're looking around, your eye doesn't smoothly swivel like a security camera. It looks somewhere, and then it jumps somewhere else. And you actually go blind for between 100 and 300 milliseconds when that happens. If you didn't go blind, you would see a big smeary mess, just like if you took a photograph while you're moving a camera. So your brain essentially turns off your vision, lies to you and tells you everything's okay, and just edits that out of your experience, and then you come back to seeing. Well, if I got 100 milliseconds where your eye is moving, and I know your eye is moving because I'm tracking your eyes really well, or I'm somehow subconsciously triggering you to look around, then that means I can do anything I want to the world for 100 milliseconds, and you'll never know. So if you're walking and you're getting close to a wall, and I rotate the world 10 degrees when your eye jumped and you went blind, it turns out if you go a small enough distance, people just subconsciously turn the other way 10 degrees. And within 3 meters, at the rate that people saccade, especially if you trigger it at a subliminal level, the rate at which you can turn people, in 3 meters, I can turn you 180 degrees. And if I can turn you 180 degrees in 3 meters, you can walk an infinite distance in a straight line in 3 meters. And so we built this whole virtual reality experience where you're walking around this very large area in this sort of western town, but you're actually standing in something that's sort of the size of a large cubicle. So we were really excited about that because it was another example of a way that we can use human perception, in some sense, against us, right? It's an optical illusion. We're exploiting limitations of human perception, but we can use it to enhance your perception of the experience. So I think that kind of result is really powerful and much more pragmatic than something like having giant multi-directional treadmills that you and your cat are standing on while you're in virtual reality. Another interesting perceptual result is, I talked about degrading images. So here's some text, and in this area, the text is at full resolution. I've actually zoomed in, so for you, it's slightly lower resolution. But when people were doing the experiment, this is full resolution, and then the text is degraded using a particular algorithm out here. And if you're probably not at exactly the right distance, but there is a distance at which if you look here, you wouldn't notice that I've degraded the text because your eye itself just doesn't have very much resolution away from sort of the central 10 to 15 degrees. Okay? So in theory, I can just degrade that and you won't notice it. We did this experiment to test the theory, and we said, okay, well, let's have people read. And if we do the gaze tracking perfectly, then they should not be able to notice this. And it turns out they don't notice it, but they read slower. So there's something going on in peripheral vision that's not modeled, or at least for the specific task of reading, that's not modeled by just the resolution of the eye. There's something that's happening in the brain as the eye is moving, maybe for high frequencies or maybe specifically for text, that needs to be understood because all these tricks like, oh, I'll just drop the resolution, apparently they affect your performance at the task and probably your comfort level. This is our Blair Witch project. Has anybody seen the Blair Witch? Heard of the? Okay, good. So we want to be able to track eyes for all the reasons I just talked about. The problem is there aren't particularly accurate gaze trackers. They're handwritten algorithms. They use cameras that are infrared and close to the eye. That's why it has these strange viewpoints. And you can write a very good algorithm for one person under one condition. But if the person's walking around a city because it's augmented reality, there's all kinds of lighting changing. You know, the person might inconveniently have makeup on or have different eye structures or have a strabismus or, you know, maybe their eyes are different colors, maybe they're wearing contacts. There's all kinds of things that take the easy case for computer vision and make it nearly impossible to sort of hand generalize. It's a great problem to solve with AI, with machine learning. The problem is to solve that, you need a lot of examples of here's a picture of the eye and here's the correct answer for where it's looking. This is for supervised learning. And the problem is it takes a really long time to take, say, 1 million photographs of people's eyes and then have, you know, someone like yourself as an intern come to Nvidia and label a little dot in the center pixel with 0.5 degree of accuracy on every one of those to train the system. And so what we did is we used GPUs in 2 interesting ways in this project. We knew we wanted to train a GPU to learn to spot eye directions and do it more accurately and faster than any previous algorithm. And we succeeded at that, and we needed supercomputer levels of processing to train it. After that, you can run it on a mobile processor once you've trained the model. But we need to get the data, and there's a chicken and egg problem of we couldn't have a machine generate the data because we didn't have an algorithm to do the thing in the first place. But we're really good at rendering at NVIDIA. Like we can make photorealistic images. So we made a model of the human eye and the human face that was photorealistic under infrared light in computer vision near eye cameras. And then we made that model so we could parameterize it. And we could change the age of the person. We could change the direction they were looking. We could change the lighting environment. We could put virtual makeup on them. We could put errors on the camera. Like maybe, you know, maybe there was a little steam on the camera and everything got blurry. And with that, we could generate millions of test images. And we had perfect ground truth data for what direction the person's looking in each photograph because we rendered the photograph in the first place. So we used traditional computer graphics to generate millions of pictures of eyes, some of which are kind of freaky looking. And then we used those to train a gaze tracker, and we made this incredibly robust and efficient gaze tracker. And then we published this whole data set because we're pretty sure that being the first ones to work on this high resolution data set, we don't think we did the best possible solution for the training. So we're hoping that others will take the data we generated in our model and use that to train even better solutions. For the focus problem, we built this large system, relatively large. It's about the size of HoloLens. And this has variable focus and gaze tracking. So as you look around, there's a high resolution inset It's higher resolution than somebody with 20/20 vision can see, so you can't possibly detect pixels. And then there's a wide field of view we fill in with a projector. So this is sort of the widest field of view and the highest resolution of any display today. And it moves with your eyes so that wherever you happen to be looking at that moment is where the resolution is. And then it can also adjust your focus level. So we're very excited about this. This was one half of our project that won the Best in Show award at SIGGRAPH this year, which we're extremely proud of. And on the other hand, we also feel like, gosh, we really wish it didn't have lots of little motors and things, because that's great for a tech demo. But now we need to figure out a way to do that without moving parts. So the solution is fantastic in terms of quality, but it's not something commercially viable. The other half is relating to this problem. There's a lot going on in this graph by Holden and others. Ignore the bars for a second. Those correspond to that axis. The lines correspond to this axis. This line is the fraction of people versus their age in the year 2000 who had myopia, right, who are nearsighted. And you can see it's here, and that corresponds to roughly, once you get above like 15 years old, it's about 30%. Here's the current projected line for the year 2050. So 30 years from now, essentially 60 to 70% of people will be nearsighted. So this is a global health epidemic. This is a serious public health problem. It is almost certainly caused by changing usage patterns with technology. It's not quite as simple as don't look at bright things or don't look at close things. There's a lot of different factors, and it's still not well understood. We do know that obviously looking at bright, close things and not being in sunlight is not great for development of eyes. That doesn't account for all the variation. But it means that, gee, if instead of looking at cell phones, I could just put that content out there in the real world and focus naturally and have it sort of intensity matched to the real world, that would probably help fight this trend. And for those of us who've been afflicted by this trend, and many of you are either wearing corrective optics or will at some point soon in your lives, we should probably also, if we make augmented reality displays, make sure that they can be prescription displays. Most current displays say you have to wear contacts if you need corrective optics. They just don't work for you otherwise. So moving the focal plane out and having it prescription was the motivation for building this display. This looks a lot like the Focals by North. It's a similar form factor. Focals is a commercial product, right? So this is research. This is not something that's ready to be sold. It weighs between 45 and 165 grams, depending on exactly what we put on it for the display. But it's very light. It's relatively comfortable. The field of view, instead of 15 degrees, is 40 degrees. So it's about, it ends up, if you take both dimensions into account, about 3 to 5 times more area of what you can see. And the resolution is massively higher. It's what we would talk about. You can't talk about pixels at this point, but it's 23 cycles per degree. So you can think of that as 60 cycles per degree is about what you can see. And so 23 is we're sort of halfway to the limit of human vision. So this is extremely interesting because these are prescription optics. We make these lenses for a specific person. They happen to cost $50,000 right now because we only made one of them. But if we made a lot of them, they may only cost $5,000. But so it's an expensive process because inside of this lens is not just a regular glasses lens. There's a waveguide and an optical combiner, and then we use holography to make some of the lenses smaller. And that allows us to make a small, compact, lightweight prescription optics. And the idea is the motivation behind this is really to address this myopia problem. So this works even if you need corrective optics. You just have it built specially for you, but it gives you a high-quality augmented reality experience. And we're also hoping that by creating technologies like that and replacing traditional displays with them, we can help solve the problem. Do I have time to briefly go through some recommendations? I don't know how we're doing on time.
We're at 2:40.
Okay.
So, yeah, I think we can do that.
Okay, so let me just wrap up then really quickly by sort of shouting out to some things. Because I walked in with my Nvidia hat on, but I want to put my academic media studies hat on for a second. Forget about Nvidia for a second. So nothing will be green for the next 4 slides. Because I want to talk about products, but I want to make clear that Nvidia is not endorsing these. This is sort of me looking at them critically. So there's a couple different devices you could go out and buy today. On the VR side, I think these are, like I showed you the HoloLens 2. and the focals are sort of two ends of the spectrum. These are sort of the ends of the spectrum for VR, and sort of the most mobile, portable, lightweight, comfortable, easy to get into system. The one that will give you the absolute peak quality, perfect tracking, very comfortable, but needs a big GPU, big desktop, and a professional system that's great if you're doing sort of design reviews, absolute peak resolution. It's a foveated display, but not suitable for entertainment or consumer use because of low frame rate and some other factors. That's the hardware. On the software side, has anybody played Beat Saber? Okay. So Beat Saber is an experience that I think is really interesting because it's a whole body experience. Even though it only has hand tracking, it allows you to move your body. You don't need to track the body to engage the body in an experience. And that sort of sounds obvious, but this is one of the first VR experiences that really did that. Many people, cross-culturally love music and dance. This is an inherent human thing. So that's a great way to build an experience, is around something that's really common. I mean, in this case, you have to really love like dance music and lightsabers, but very cross-cultural common. It's very scalable. It's abstract, so it can start as mobile experience and go all the way up to a high-end VR experience. And you're essentially dancing and slashing, almost like playing drums against these flying notes that are coming past you as a rhythm game. And it's very short. So for a VR experience, especially with a concern about either fitness or comfort, allowing people to get in quickly and then either get out or have effectively as much replay as they want by just going through multiple songs. So sort of the ideal VR experience. And I think that's been reflected in its sales. Lone Echo, I would say, is the best narrative experience I've had in VR. Very long form, like something like 10 or 20 hours across multiple sessions. This is the game that's in space, and so the way you move around is by grabbing things. You can only get away with this once, but they were the first ones to get away with it. And so it feels very natural that you can locomote around an entire space station without having to physically walk in space. So it works as home VR. It's also the first game where I felt like there was an NPC, a non-player character, who had presence, who I felt was really there, and I was interacting with as if they were a human. Ironically, you're playing a robot. so the robot is playing the human, and the human is playing the robot. And just sort of a brilliantly designed game narrative experience that I think is one of the few, really. Secrets of the Empire is interesting because this is an installation experience. Has anyone done this? It's in Toronto. Okay. I think it's like $20 for 15 minutes in downtown Toronto. You go into this place, you dress up nominally as a stormtrooper. Really, you're putting a lot of computer stuff on you. You don't look anything like a stormtrooper. But when you put the headset on, there are physically other people who are in the real world sitting next to you who you will see wearing a costume, and they're tracked. You're holding props, like you're holding your laser blasters. And this is the one where you're walking around a warehouse, and when you touch a wall, there's really a wall there. Having multiple real people in a physical space, right? This is really like sort of the limit of interactive theater or live action role playing. It doesn't matter the graphics are great, but it doesn't matter. It doesn't matter that it's Star Wars and the music is good. The fact that there are real people in a real space makes that an amazing experience. This is sort of the most powerful thing you can do to make the virtual real. Oculus Medium is a professional tool for 3D sculpting. People are now using it for character design and actual asset creation. And I think it's important to say that the applications that I think will really carry VR, at least in the short term, are professional creative applications. It's not about entertainment. And Google Earth VR, which is another killer app, recognizing that it's not about graphics. It's not even about interactivity in the sense of things react to you. It's interactive in the sense that you can move around. But this takes a database of the entire world and lets you explore it. And this is just such a natural fit. VR succeeds when there's a reason for VR, not when it's being forced onto something. And so this is an experience that takes the best possible content that feels practically infinite, although it's obviously a fixed database, and lets you explore it and explore natural, and take your friends on tours and look at the area you're about to move to or go on vacation in. And so this just really takes, it's like cooking, like just take wonderful ingredients and then let them shine through. So I think those are sort of powerful lessons that I think everyone should learn from those experiences. If you're interested in making VR content and you haven't done so before, I recently came across this great course made by Unity and Oculus which is online and it's free. And essentially, you could spend $250, get the lowest end Windows mixed reality headset, take that course over the course of a couple hours in a weekend, and you could be creating VR experiences yourself. So to wrap up, we've seen first-gen VR and AR, which is about coming. First-gen VR is getting pretty mature. There's a bunch of headsets that all have similar specs and kind of do the similar things. AR is coming, but as just sort of notifications that float, like an Apple Watch for your face. That's what focals are. There are several other products in that space. It doesn't have 3D tracking and embedding and all the things that we're envisioning, which HoloLens can do in limited ways, but is not widespread. The big challenges are getting VR to be comfortable, just to be someplace where people can actually use it, where it doesn't interrupt their workflow. And that's going to be heavily about perception and using the body. It can't be about having a monitor that moves around with you. It has to be more than that. For AR, tracking is a problem, cloud is a problem, and just the technology of the display itself is a challenge. On the content side, which is where I think many of the interesting problems for you folks are, narrative challenges in AR, except for Lone Echo, I haven't really seen good narrative experiences. There are a lot of VR films. Some of them are quite good. Every good VR film I've seen, I think, would have been better as a well-directed traditional film. No one has quite cracked, in my subjective eyes, how that medium should work. I think that having the disproportional advances in artificial intelligence recently might be a way to fix that. Partly interaction with characters, but partly just having an AI director so that when you go off script, the world and the story can adapt to you is a huge piece of that. And I think the locomotion schemes, which are kind of sketched out, I think there's still a lot of interesting ideas there. There was a time when we thought it was going to be all about you're standing on treadmills, and we're quickly finding all kinds of interesting things, whether it's the wheelchair floating in space. Maybe some of those are generic, or you can get people to just sort of be happy with that as a medium, or the redirection and those kind of ideas. Some of them even go further. They put little electrodes on you and manipulate your motor, your actual muscles themselves, so that they can literally steer you, not just perceptually steer you. There's a lot of space out there for interesting things. All right, thank you very much.